Hello, in this video we're going to be solving this minimization problem using the Simplex algorithm. Well, to find the minimum to this LP, we're going to be solving this equivalent LP, which is a maximization problem. As you can see, the two LPs are pretty much the same except for the objective function. So this minimization objective function is equivalent to this maximization objective function. As you can see, this one is this objective function multiplied by -1. And also, as you can see, we haven't touched the constraints at all. They do not represent a value. They represent a feasible region. So we leave them as they are. So to start our simplex algorithm, we need first of all to write our LP in the standard form. So we added S1 and S2. And as we usually do, we start our algorithm by setting our original variables x1 and x2 to 0 and putting S1 and S2 in the basis. So S1 and S2 here. The coefficient in the objective function is 0. So we have 0 here and 0 here. And here we're going to be putting the coefficient of the variables in the constraints. So here we have 1, 1, and 1 for S1, 0 for S2. The value is the right-hand side of the constraint. So here we have 10. We do the same for the second constraint. So 1, -1, 0, 1, and the value is 2. In the C-bar row, we're going to be putting the coefficient of the variables in the objective function, in this objective function. So we have 3, -1, and 0, 0. Okay, so to proceed, we need to find out which variable is going to be entering the basis and which variable is going to be exiting. So to choose the entering variable, we're going to have to select the variable with the largest C-bar value because that's the variable that's going to add the most to our objective value. So x1 is going to be the entering variable, and hence this column is going to be called the pivot column. Okay, so now we need to determine which variable is going to exit the basis. To do that, we're going to calculate the ratio, and it is calculated by dividing the value by the equivalent value in the pivot column. So okay, so as you can see, S2 has the smallest ratio, so we're going to be selecting it to exit the basis. So S2 is going to be exiting, and hence this row is going to be the pivot row, and this element is going to be the pivot element. We forgot to put in the value of z in this iteration, so we're going to do that by using sum product. So the value of z here is 0, and now we're going to move on to tab 1. Okay, so to fill in tab 1, first thing we're going to do is to put the entering variable x1 in the place of s2, which is the exiting variable. Its coefficient in the objective function is 3, so we're going to put 3 here. Okay, so we're going to fill in this row, and it's filled in like this. We just divide each element in this row by the pivot element, which is here is 1. So we're going to have 1, minus 1, 0, 1, 2. Now we're going to put in zeros for the variables in the bases. So for x1, have zeros here, and for s2, I'm going to have zeros in here. Sorry, I mean it's s1, so we have s1, 0, 0. And for the rest of the cells, we're going to be using the rectangle method. So this element is equal to the original value minus this value in the pivot column multiplied by the value right next to the pivot element, and we divide by the pivot. So I just went ahead and filled in the rest of the values in the tableau. And as we can see here in the C-bar row, we still have some iterations to go through since we have a positive number here. So x2 is going to be our exiting variable for the next iteration. As usual, we calculate the ratio. We don't put anything here because we have a negative number. So S1 is going to be the exiting variable. So from here on, we're going to be doing the exact same thing we did in the previous iteration. So this is tab 2. As you can see in the C-bar row, we only have zeros or negative numbers. So we have reached optimality, and the objective value is 14. x1 is equal to 6 and x2 is equal to 4. So here, x1 and x2 are the optimal values. However, the optimal value of z is actually minus 14. As mentioned earlier, z is the objective function of the original minimization LP, and z prime is the objective function of the maximization LP, the equivalent maximization LP. So here we have solved for z plus. So this is the value of the optimal value of z plus, and the optimal value of z is actually the value of z prime multiplied by minus 1. So that's how we solve a minimization problem using the simplex algorithm. This is not actually the only way to do it, but I find this to be the easiest way. So let me know if you have any questions, and thank you for listening.